Welcome to this specialized training module titled Climate Factors in Urban Density Design, developed as part of the EPD-Net project. This initiative, supported by the Erasmus Plus program, focuses on filling the gap by creating an ecological planning and design learning network. As our global climate changes, the way we design our cities must evolve. We are no longer just building structures, we are crafting adaptive environments. This module is designed to provide you with an integrated approach to disaster-resilient and sustainable urban development. We will explore how urban density, often seen as a challenge, can actually be a tool for climate adaptation when guided by smart training and ecological principles. Throughout this session, we will examine the vital intersection of architecture, climate science, and urban planning. Our goal is to empower you with the knowledge to build the smart, sustainable cities of tomorrow. Let's begin our journey by looking at the core climate factors that shape our urban density. In this module, we will explore the relationship between urban density and climate through a structured and progressive framework. We begin by outlining the learning objectives, clarifying what you are expected to understand and apply by the end of this session. Next, we introduce the fundamental connection between urban density and climate, examining how spatial concentration influences environmental performance. We will then identify the key climate variables affected by urban density, including temperature, airflow, solar exposure, and energy demand. Building on this foundation, we will discuss design parameters for optimizing climate-responsive density, focusing on how urban form can be shaped to improve environmental performance. However, increasing density always involves compromises. Therefore, we will examine the trade-offs in climate-responsive density, addressing both benefits and potential challenges. To ground theory in practice, we will review case studies and practical applications, demonstrating how these principles are implemented in real urban contexts. Finally, we will summarize the key messages and provide references for further exploration. Let us begin by defining our learning objectives. By the end of this module, you will achieve three main learning outcomes. First, you will understand how urban density interacts with key climate variables. This includes recognizing how compactness, building height, spacing, and urban form influence temperature, airflow, solar exposure, and overall environmental performance. Second, you will be able to identify the key design parameters that help optimize climate-responsive density. Rather than viewing density as simply high or low, you will learn how it can be strategically designed to improve environmental quality. Third, you will evaluate the trade-offs between compactness and climate performance. Urban density can support energy efficiency and land conservation, but it can also create challenges related to ventilation, shading, and urban heat. These objectives will guide our discussion throughout the module and help you critically assess urban design decisions in relation to climate. Urban density should not be understood only as a numerical value or a spatial measurement. It is not simply about how many buildings or people occupy a given area. In reality, urban density directly shapes microclimate conditions within cities. It influences thermal comfort, airflow patterns, solar access, shading, and the accumulation or dissipation of heat. The way buildings are arranged affects how wind moves, how surfaces absorb radiation, and how heat is stored or released. Therefore, climate-sensitive urban design requires us to understand density as a morphological system. Building form, height, spacing, orientation, and street layout interact continuously with local climate factors such as sunpath, prevailing winds, and seasonal temperature variations. Instead of asking only how much to build, climate-responsive planning asks a more critical question: how does urban form perform under specific climatic conditions? This shift in perspective, from quantity to performance, is fundamental to designing climate-responsive density. Urban density influences several key climate variables, and understanding these relationships is essential for climate-responsive design. First, solar radiation is strongly shaped by urban form. Building height, spacing, and orientation determine how much sunlight reaches streets and facades. The height-to-width ratio of streets affects shading patterns, while excessive obstruction may reduce solar access in colder climates or increase overheating in warmer ones. Second, temperature and the urban heat island effect are closely linked to density. Compact urban fabrics can increase heat storage due to surface exposure and material properties. At the same time, vegetation ratios and nighttime cooling capacity significantly influence how heat is retained or released. Third, wind and ventilation are directly affected by spatial configuration. Block permeability, the presence of wind corridors, airflow patterns, and overall urban porosity determine whether a city promotes natural ventilation or creates stagnant air zones. Finally, humidity and precipitation management depend on surface characteristics. Permeable surfaces, evapotranspiration from vegetation, drainage systems, courtyards, and open spaces all contribute to how water is absorbed, retained, or redirected in dense environments. Together, these variables demonstrate that urban density is not only a spatial condition, but also a climatic regulator. Solar radiation is one of the most critical climate variables affected by urban density. Building height, spacing, and orientation directly influence solar access and shading patterns. The arrangement of buildings determines how much direct sunlight reaches facades, streets, and open spaces throughout the day and across seasons. In high-density environments, solar gain may be reduced during winter, potentially increasing heating demand in colder climates. However, in hot climates, the same compactness can provide beneficial shading, reducing overheating and improving outdoor thermal comfort. An important parameter in this context is the street-canyon proportion, commonly expressed as the height-to-width ratio, or H/W ratio. This ratio controls both the duration and intensity of sunlight penetration into urban spaces. Narrow canyons with tall buildings create longer shaded periods, while wider streets allow greater solar exposure. Therefore, solar performance in dense environments depends not only on how much we build, but on how we configure urban form in relation to climate. Wind and ventilation are highly sensitive to urban density and spatial configuration. Dense urban fabrics can either block wind or channel it, depending on how buildings are arranged. Continuous and compact blocks often reduce airflow, creating stagnant air zones and increasing heat stress, especially during warm periods. When ventilation is restricted, accumulated heat cannot dissipate efficiently. This not only affects outdoor thermal comfort but can also increase cooling demand in buildings. On the other hand, permeable layouts, staggered building forms, and strategically positioned open spaces can enhance natural air movement. Wind corridors, gaps between blocks, and variations in building height help guide airflow through urban areas. Therefore, the goal is not simply to reduce density, but to design it in a way that maintains urban porosity and supports effective ventilation under local climatic conditions. Temperature in dense urban areas is strongly influenced by the urban heat island effect. Dense environments tend to store and re-radiate heat due to several interconnected factors. First, high building mass increases thermal storage. Materials such as concrete, asphalt, and stone absorb solar radiation during the day and gradually release it at night. This slows down cooling processes and elevates nighttime temperatures. Second, reduced vegetation limits shading and evapotranspiration. Without sufficient green areas, surfaces are directly exposed to solar radiation, and the natural cooling effect of plants is diminished. Third, limited nighttime cooling further intensifies heat accumulation. In compact urban fabrics, restricted airflow and trapped radiation reduce the city's ability to dissipate heat after sunset. As a result, dense areas often experience higher average temperatures compared to surrounding rural zones. Understanding these mechanisms is essential for designing density that mitigates, rather than amplifies, urban heat stress. Urban density also plays a significant role in regulating humidity and precipitation dynamics. In high-density environments, the reduction of permeable and green surfaces limits evapotranspiration, which is a key natural cooling process. When soil and vegetation are replaced with impervious materials such as asphalt and concrete, rainwater cannot infiltrate the ground efficiently. This not only decreases moisture retention but also weakens the natural balance of local humidity. Urban form also influences rainwater runoff patterns. Compact and highly sealed surfaces tend to accelerate surface runoff, increasing the risk of flooding and reducing groundwater recharge. The spatial arrangement of buildings, streets, and open areas therefore directly affects local water management. However, integrating courtyards, permeable surfaces, and open spaces within dense urban fabrics can improve microclimatic comfort. These elements enhance moisture balance, support evapotranspiration, and contribute to more resilient urban water systems. For this reason, climate-responsive density must consider not only heat and airflow, but also water and humidity dynamics. Designing climate-responsive density requires moving from analysis to strategy. The first parameter is density configuration. This includes floor area ratio, building coverage, and the relationship between height and spacing. Density is not only about how much is built, but how built volume is distributed in space. Second, massing and layout play a crucial role. Building orientation, alignment with prevailing winds, and appropriate setbacks determine how urban form interacts with sun paths and airflow. Third, solar control must be carefully managed. Street proportions, building heights, and facade exposure influence both shading and solar access. The goal is to balance winter solar gain with summer protection. Next, ventilation strategies focus on urban porosity and block permeability. Integrating wind corridors and allowing air movement through and between buildings helps reduce heat accumulation. Thermal regulation is another key parameter. Material selection, surface reflectivity, and the integration of vegetation significantly affect heat absorption and release. Finally, open and ground spaces such as courtyards, permeable surfaces, and connected green areas enhance microclimatic comfort and water management. Together, these parameters demonstrate that climate-responsive density is a design challenge, one that requires careful coordination between form, performance, and local climate conditions. This diagram is a visual summary of the design parameters we just discussed. Rather than introducing new concepts, it organizes the previous content into a structured framework. It shows how climate context, including solar radiation, wind, and temperature, interacts with key urban density parameters such as configuration, massing, solar control, ventilation, thermal regulation, and open spaces. The diagram also highlights an important idea. Density should not be treated as a single numerical parameter, but as a combined morphological system. In other words, optimizing density means adjusting urban form in response to specific climate conditions. Moving forward, we must understand that climate-responsive urban density is not about finding a single perfect solution, but rather about managing a delicate balance of competing environmental effects. In urban design, improving one aspect often directly influences others, making conscious trade-offs an essential part of the planning process. Let's look at some of these critical balances. First, we have compactness versus ventilation. While a compact city reduces travel distances, it can also block essential wind paths that cool our streets. Similarly, we face compactness versus solar access. High-density buildings can provide necessary shade, but they may also prevent natural sunlight from reaching lower levels or neighboring spaces. Furthermore, we must weigh shading versus heat reduction and ventilation versus heat control. Every decision to block the sun or invite a breeze affects the overall thermal comfort of the urban fabric. As designers, our goal is to navigate these trade-offs to create environments that are both efficient and livable. Understanding these dynamics is the first step toward a truly resilient urban form. In this section, we explore the critical tension between high-density urban forms and natural air circulation. On one hand, high compactness is a key goal for land efficiency. By building densely, we reduce urban sprawl and maximize land use. However, as you can see in the illustration, this density often comes at a cost. It restricts wind flow and traps heat within the building clusters, leading to significant heat buildup and the urban heat island effect. On the other side of the spectrum, we have good ventilation. This approach utilizes a more permeable layout, characterized by strategic spacing that channels wind through the city. These wind paths are essential for heat dissipation and providing better natural cooling for residents. The challenge for modern ecological planning is not to choose one over the other, but to find a design synergy. We must ask, how can we maintain high land use efficiency while still creating a permeable urban fabric that allows our cities to breathe? Balancing these two factors is vital for ensuring both the density our growing populations need and the thermal comfort our climate demands. Next, we examine the relationship between urban density and solar exposure. While high compactness is essential for efficient land use, it creates a significant challenge for solar access. As shown in the left illustration, dense building forms naturally increase shading. In summer, this can be an advantage by reducing heat, but it often leads to limited daylight and a loss of vital solar gains during the winter months. High land use efficiency here must be weighed against the potential for deep shadows that can make indoor and outdoor spaces less comfortable. On the right, we see the alternative, better solar access through an open layout. By strategically spacing buildings, we allow the winter sun to reach the ground and building facades, while still providing good natural daylight throughout the year. This open configuration supports energy efficiency by reducing the need for artificial lighting and heating. The goal for climate-responsive design is to find the sweet spot, designing compact areas that utilize smart orientations and varying heights to ensure that even in a dense city, the sun remains a shared and accessible resource for everyone. Another fundamental trade-off we must navigate is the relationship between shading and heat reduction. In hot climates, providing ample shading is one of our most effective tools for lowering thermal stress at the street level. By blocking direct sun exposure, we create cooler microclimates that protect pedestrians and reduce the energy needed to cool nearby buildings. This summer priority approach is essential for urban resilience in the face of rising global temperatures. However, design is a seasonal challenge. As shown on the left, an environment with more shading can become a disadvantage during colder months. Excessive shade can lead to a winter chill, creating dark and less comfortable outdoor conditions when we actually need the sun's warmth. The key, therefore, is finding a balance that offers thermal relief in the summer without sacrificing comfort in the winter. We must aim for adaptive shading strategies, such as using deciduous trees or smart architectural overhangs, that respond to seasonal impacts. Our goal is to ensure that heat reduction efforts today do not lead to unintended discomfort tomorrow. The final trade-off in our series explores the dynamic between ventilation and heat control. As we have seen, maximizing airflow is a powerful strategy for natural cooling. By designing urban corridors that invite wind flow, we can significantly lower temperatures during hot summer months and improve overall air quality. This cooler summer approach is a cornerstone of sustainable urban design in warmer regions. However, we must also consider the needs of colder climates or winter seasons. As illustrated on the right, high ventilation can become a liability when we need to retain warmth. Increased airflow can intensify heat loss from buildings, making it harder to maintain comfortable indoor temperatures and increasing energy demands for heating. In these cases, heat control becomes the priority. By strategically blocking harsh winds and focusing on thermal insulation, we protect the urban environment from the cold. The ultimate challenge for a climate-responsive designer is to create a flexible urban fabric, one that breathes when it's hot but provides shelter and warmth when the temperature drops. Balancing these two forces is essential for year-round urban comfort. To see these principles in action, let's look at a world-class example: the Ecological district in Barcelona. This district is a masterpiece of climate-responsive morphology, specifically designed to handle the Mediterranean climate's high summer solar exposure. The core idea here is how urban form can actively mediate sun, air, and heat. The layout uses a medium to high-density orthogonal grid with a unique feature: interior courtyards within perimeter blocks. These courtyards are not just aesthetic, they are functional lungs for the city, providing essential ventilation and private green space. Furthermore, Barcelona's planners utilized controlled building heights and wide streets to maintain an optimized height-to-width ratio. This careful calibration ensures a perfect shading balance, offering relief from the intense summer sun while still allowing daylight to reach the street level. In our example, density is not an obstacle to comfort. Instead, the geometric precision of the urban fabric serves as a natural climate regulator, proving that smart design can make high-density living both sustainable and highly livable. Continuing our analysis of Barcelona's Ecological district, we focus on the specific climate performance outcomes of its unique geometry. The district's famous street canyons are meticulously designed to provide controlled solar access, ensuring that sunlight reaches the lower levels without causing extreme heat gain. One of the most brilliant features of this layout is the use of interior courtyards, which serve a dual purpose. They facilitate natural daylighting for every apartment and enable essential cross-ventilation, allowing the buildings to breathe naturally. Note the iconic chamfered corners of the blocks. These are not merely for traffic visibility, they significantly improve airflow at intersections, reducing the stagnancy of air. This compact form is a winter asset as well, as it reduces overall thermal loss. In the summer, the shared shading provided by the dense configuration effectively mitigates overheating at the street level. The key insight here is clear: urban density performs climatically only when its configuration responds directly to its local context. Our example proves that density, when well designed, is a solution rather than a problem. As we conclude this module, let's synthesize the core principles of climate-responsive urban density. The most vital takeaway is that urban density directly shapes microclimate conditions. It is not merely a mathematical number, but a matter of form and morphology. Factors like building height, spacing, layout, and openness are the real drivers of environmental performance. We have seen that while compactness is essential for land efficiency, it must be carefully balanced to prevent the loss of ventilation and solar access. True climate-responsive design is never about maximizing one single element, like shading or airflow, in isolation. Instead, it is about the art of managing trade-offs. It requires us to avoid extremes and find the strategic middle ground that serves both summer and winter needs. Ultimately, optimized density means adapting the urban form to its specific local climate conditions. By applying these integrated design strategies, we can transform high-density areas into resilient, comfortable, and sustainable living spaces. Thank you for participating in this EPD-Net training module. Together, let's build cities that breathe and thrive.